use the proton beam from LANSCE to create the intense?
No, so it will be a separate accelerator that's run on the north side. We'd like to keep running LANSCE at the same time so that as we're interrogating materials with these X-rays, we can also simultaneously interrogate them with the protons. So we radiograph dynamic events now with the proton beam. Protons and electrons and X-rays do different things, right? The protons can penetrate a lot more material than the X-rays can. And so you can see things that are happening deep inside of the material at the same time as you're studying what's going on at the surface of the material and the grain structure with the X-rays. And being able to do those two things simultaneously, we think is very important for understanding how these materials are going to behave. Yes?
Actually, I have another question, but this one just made me wonder, is curious if that related then, this new facility, does that have anything to do with the substation upgrade that they're working on now?
So,
it seems like you're going to need
so
more power.
the substation upgrade right now, we're going to need some more power, but actually the substation that we have can supply enough power for both Marie and LANSCE, but if part of it goes down, then we'll have problems. So they're going to upgrade the substation to give us some backup capability. The main point of the current upgrade is for the computing center that's going on. For exascale computing, they need a lot more power up at TA3, and that's the reason for the current upgrade. Yeah.
So my real question then had been kind of related to Linda's. You said that this one point was where they took the takeoff for the Lujan building, and you mentioned earlier that at one point all 16 beams were being used there.
Yes.
I'm wondering what's magic about the 16 beams, because now it's still 16 beams limit, but they're all over the place now. So what's magic about 16? Can you do more than that, or?
So, I mean, there's nothing really magic about 16. That's how, we had different flight paths, had different instruments that were specialized to make different types of measurements, right? And so the target we had, and this is something that I didn't mention, but it's a very complicated target, and just like with the ultra-cold neutrons, depending on how we call that neutron moderation. When you go from a high energy neutron to a lower energy neutron, we call that moderating the neutron energy. The moderators in the target in the Lujan Center are very complicated. So there are several of them. There's a water moderator, and that makes neutrons that have energies kind of room temperature, thermal neutrons we call them. We also had liquid hydrogen moderators, okay, and those made neutrons that had milli-electron volt energies, 1,000th of an electron volt. The thermal neutrons are used to do neutron diffraction. And so you make a material, and let's say you take two pieces of metal and you weld them together, right? When you make that weld, you actually stress the material. Okay, and then as the material cools, it tries to relieve some of that stress, but there's still some residual stress in there. And you want to measure that to understand about the engineering of doing that weld. And so what you do is you put that in the neutron beam, and the neutrons would form a diffraction pattern. And by measuring that diffraction pattern, it tells you what the spacing is between the atoms in the metal. Okay, and that spacing, as it changes, tells you what the stress fields are in that material, right? So when you take just a plain sheet of metal, you'll see a certain spacing, and then if you push on it or pull on it, you'll change that spacing, and that's the stress field in there. And so the higher energy thermal neutrons go through the material, and so you use those to measure that diffraction pattern and look at things like residual stress in materials. One of the very interesting experiments that they did there had to do with something like the Golden Gate Bridge, right, where you have these giant cables that are actually made up of thousands of smaller cables. One of the big unknowns they had was if one of those small wires breaks, what happens to the strength of the big cable that's holding the bridge up? And so they had thought that you actually lost quite a bit of strength, that you had to move, there's friction between them, but they thought you had to move very far away before you lost knowledge of the fact that this one wire was broken. And so they took some smaller cables down to the Lujan Center and put them in one of our neutron diffractometers, and they made some cuts in there, and then they could see how that residual strain field was as you went away from the cut. And what they found out was actually the the cable did not lose as much strength as they thought it would if you cut one of the wires. And so it turns out that the Golden Gate Bridge would probably last a lot longer before you had to do a cable replacement. And then, just 1 second, and then the lower energy neutrons, what you use them for is scattering off of an interface or a material. Okay, the lower energy the neutron, the easier it is to scatter off of a material. So when you want to study the surface of a material, or if there's a layer that's buried and you want to understand that layer, you do these neutron scattering experiments, and that's what you use the lower energy neutrons for.
I think these real life examples of what you've used LANSCE for to understand, I mean, that every single person who hears about it can relate to, rather than maybe, yes, fundamental understanding of the workings of the universe is great, and we all want that, but these practical applications really bring it home. Are there some sort of general categories of work that's done at LANSCE? You've talked about the medical radioisotopes, that's fantastic, and you just talked about materials for like analyzing their use in structural engineering. Can you cite a few others that resonate with us and what at LANSCE is being employed?
So, I'm not sure how much it'll resonate with you, but so the proton radiography facility is, I don't know if people know about DART, right? So DART is a big X-ray machine at the laboratory, and it radiographs implosions of devices. So the thing about X-rays is it's very hard to get multiple pulses, and X-rays are very also hard to penetrate thick objects. Protons penetrate objects much easier. Protons, from the accelerator, you can get a pulse structure on demand. So you can make a movie of a dynamic object that happens over short time scales or long time scales. So in the proton radiography facility, we have kind of a minimum time between camera frames watching an implosion of something like 100 nanoseconds, 100 billionth of a second. And we can keep watching things for hours if that's what it takes. In some experiments we do that. Other experiments are over in a few microseconds, right? And so what we do there is you take these protons and you have a very fast imaging camera, and you can watch this object implode, or you can take a piece of high explosive and you detonate it, and you watch how that detonation front moves through the high explosives. And so actually understanding the behavior of high explosives is one of the main drivers of the proton radiography facility, because for obvious reasons, high explosives and their performance are very important to the laboratory. And in some sense, it should be important to all of us, because one of the biggest safety improvements in nuclear weapons was moving from what they call conventional high explosives to insensitive high explosives. So I recently read a book called Command and Control. So I don't know if anyone here has read that book, but if you have, it'll scare the crap out of you, right? I mean, just the fact, with the original nuclear weapons, if you dropped them, the high explosives could go off. Right? Now, then they had to worry about, are these things 1 point safe or not, right? So they've had events where they dropped them and they melted a bunch of plutonium and it scattered in the environment, right? So the move from conventional high explosives to insensitive high explosives, to me, was a huge improvement in the safety of the stockpile. But insensitive high explosives don't burn the same as conventional high explosives. So understanding how that burns and being able to design a weapon that uses the insensitive high explosives, PRAD, the proton radiography facility, was very important to that effort.
Was that part of the refurbishment of the stockpile, being able to replace perhaps one high explosive that's in an aging warhead with a new